Welcome everybody. We are going to talk about how to break security features of an SoC, a system on chip, which I will refer to as a SoC from now on, without having basically a vulnerability in the implementation like Laura in the talk before presented. A bit of introduction, just to give an idea of the, where I am. Well, actually this research has been done with my partner, Nick Timmers, and we are both co-founders and security researchers, and we have quite some experience in the field now. I would say that the last 15 years of my life have been spent in tearing apart devices, breaking SoC in different ways, and let's say having fun along the way. And so far so good, I would say. And if you want to know a bit more, there is our blog on Realize, and we cover let's say whatever is in between hardware and software. We like to cover things which are the finished devices or trusted execution environments, secure boot. So whatever is a low-level software or hardware is something that we are interested in general. For SoC security, well, the security features of an SoC are become just increasingly relevant. As we have seen, even in a previous talk, they are becoming very common also on low-cost system on chip nowadays. And here there are a few examples. I mean, there is the very well-known chip from Espressif, which has flash encryption, secure boot, signatory verification, then crypto engines, and same goes also for microchip. There we find other examples over here, Citara processor, and finally also the NXP one. So all these processors, all MCUs are not overly expensive. They are definitely accessible, and that's why the OEMs in general are starting to consider the security feature as part of the use case. For example, for sensitive and critical device-based services, IP protection in general. These are just a few examples that come to mind, but in general it's clear that the security of system on chip is becoming more and more important. And same goes also for fault injection, because the concept is becoming now familiar to security researcher. There is more accessible tooling, and you see here Chip Shower and Pico EMP, some fun tool definitely to have and to play with. And there are advanced techniques which are presented at public security conferences, hardwear.io, and hopefully also this talk, we'll see. What I think is missing in the field. I think there is a bit of systematization of the field in fault injection, which is actually missing. And we mostly have research from security community, from academia, and from industry labs that are still, let's say, going in parallel, but not necessarily always merging. And we had realized we try to make that happen as often as possible. So the goals for our talk is that we want to show how SoC security depends in general on OTP data. So basically we'll start from really the basic, from understanding how this works. We want to present fault injection attacks in a more systematic way. We actually target transfer of data from OTP. I'd like to share our results, which we achieved using EMFI on ESP32. We'll see that in a moment, and also discuss briefly possible countermeasure here. But in general, this talk is intended to contribute to the field. We are not here necessarily for the, we broke a great chip, but maybe we think that this technique could be applicable from here to the next 10 years. So to give you a bit of context here, in 2019 we presented a secure boot talk at Blue at Israel. It was February 2019. We bypassed an encrypted secure boot on stage. Well, we happen to love live demos in general, so I mean we were really happy to do so. But in the meantime, along the lines, we also described the fault injection attacks which were targeting OTP transfer. It was just generic. It was mostly theoretical at the time. Well, actually we knew it could work. That's why we shared that part. But we don't have a demo or research ready for that. The concept is not specific to an SoC. So whatever we are saying in this talk is not specific to this, conceptually, to this system on chip we are going to present, which is going to be the ESP32. It's a very popular IoT system on chip. When it came out, it's been extremely popular in several applications. It's an Extensa, like 6 CPU. It's internal, external memory. It's very rich feature. Which feature rich SoC in terms of support for Wi-Fi, Bluetooth, and a very rich API. So it's really useful, usable actually, I would say. So this is the module that you see, and in this module, which costs around, I would say, between depending on $7 and $15, you have secure boot, flash encryption, and support for disabling of JTAG, and even a few more security features, but these are the ones that we are interested in, and in extremely low price package. So this is really available to, I would say, to everybody. So this generated lots of interest, also from a research point of view. Hey, we have something nice that does not cost so much, and we can actually play and try to break. We were not alone, of course, in doing this. Actually, Limited Results did a great research and performed multiple fault injection attacks towards this chip, ESP32, mostly based on VCC, on voltage glitching. They target the AES crypto core first, mostly the driver. So basically by glitching, if I remember correctly, they could set the key to 0, or they could skip the encryption entirely, but it was still targeting the driver logic for driving the crypto engine. There's been also secure boot bypass, still in terms of software being executed. And there's been also dump on OTP protected keys. Basically, the secure boot and flash encryption on this chip are based on secrets keys, which are both symmetric. And the secrecy of this key is confidentiality is extremely relevant in order for this security feature to actually make sense. And this attack, I'm not sure if it was, I think it was intended, indeed targeted an OTP data transfer. And we are going to see that in a moment, but basically I think it's the first public implementation of the attack that we were just describing a few months before. Not sure if there is any relationship or it's been done intentionally, but it was nice to see that maybe the time were mature for this kind of attacks. We actually did also some EMFI attacks. The difference is that we performed all our attacks through EMFI. Why? Because we don't have to solder, we don't have to decap, we don't have to do anything. We are really low with EMFI, and that's why. We bypass secure boot. We do this usually with different techniques. We don't bypass the mem compare or the signature verification. We don't care about that. We usually take PC control via MMCPY. So in a nutshell, we control the data, and while this is being transferred, we glitch, and the data we are transferring goes to program counter. So at that point, we can go anywhere. So basically, we achieve a perfect PC control via what is called the instruction modification. It's a fault model that is being, Mark, we presented that in 2015 or 16, I think, and it was the first time that we actually came out with such an idea, and it works beautifully, and it's our fault model of preference nowadays. With the same, by using instruction modification, we also bypass the flash encryption, and so we do that also together with secure boot. Basically, with PC control coupled with SRAM data persistence, we were able to switch the chip to a different stage while still controlling program counter, and this allows with a single glitch attack to bypass the secure boot, to bypass the flash encryption, so access plain text data without knowing the key. That's the important part. We don't need to dump the key with this kind of attack. So if you need more, these are links. It's an old research nowadays, but the links are there. Please do that. So let me go back to our guest of today, which is the one-time programmable memory, or also called OTP. Let's start from the basic, from the memory cell. And the basic idea is that you have memory where bits can be set only once and cannot revert to the previous state. And this is achieved by physical modification of the cell. For example, what you see here is a programmable poly eFuse. So this is also called fuses. These are called the eFuses memory. There are several names to this kind of memory, OTP and all these things, but the basic concept is that it is a cell that you physically modify in order to represent a bit. But because it's been physically modified, it cannot be reverted back. So, for example, what you see is that here the path has been actually blown. That's where the name will actually blow a fuse. In case of secure variants, as far as we know, there are no observable difference in programming. So while this is visible optically, or at least with a microscope, generally at the same level of visibility here, this is also programmed, but you don't see actually a break. This is called anti-fuse. Again, if you need more, there are links. This is just to give you a sketch, the landscape of OTP. So there are memory cells which actually represents bit. Typically, an unprogrammed cell represents a 0, and when you blow it, when you physically damage it, it represents a 1. Keep in mind that this is usually done like this. Sometimes, I've seen situations which actually were broken, so it's a bad idea to do so, where 1 is unprogrammed and 0 is programmed. If you do this way, I mean, this could be a big security problem. But in general, OTP contains data. You should think about as non-volatile memory, which is non-volatile forever, more or less. It contains data, configurations, configuration data, or secrets in general, keys. This is an example which I likely found over the internet that shows you that actually the cells are organized in an array. There are several lines of decoder in order to access it. And also, you're going to need a write line which actually provides higher voltage in order to break that physical, to damage that cell. But you see that basically the density can be, well, pretty decent, I would say. And this is actually the core where the data is stored. Okay? Now, the data is not stored randomly. There is a nice organization of memory. So the OTP is typically divided in regions. There are regions where you can control a single bit. So basically you can read a single bit, you can write a single bit, and without affecting the rest. This is typically used for security configuration. Like I want to set up disabled JTAG. You blow just one single fuse, one single bit, and then from that moment, the logic will lock JTAG. We'll see how in a moment. But also, there are possible that you have blocks where you actually can only write multiple bits at the same time, and when you read them at the multiple bits at the same time. This actually depends how the block is wired in general. And this approach used for bulk data, like keys and so on. Important part is that regions themselves can be read and write protected. So the region can be read locked or write locked. This is actually the typical jargon that you hear, but in practice is read and write protection. So this means that somewhere else there is an OTP bit that if you actually set that to 1, then the corresponding regions become read or write protected, depending on which bit you actually set. Why this is needed? Well, the main point is that if you have keys, the keys are not just made of ones. There are ones and zeros. But by nature of the OTP, by technology, the 0 can always be brought to a 1. It's only the opposite is not. So in order to preserve a value of 0, that you want that to be at 0, you need to lock that region. Because if you don't do, for example, one interesting attack is that I could write one single bit in your key or one single block. Chances are is that the resulting public key will be much weaker to factorization. I mean, in general, the strong keys are very rare. The one is strong, and they're not close to each other. So if you change one bit in a very strong key, there is a high chance of mutating that in a very weak key, which you can then factorize. You can then create a private key and then buy. I mean, just a nutshell how you could use this and why it's important that you actually preserve those zeros to zeros, especially for keys. So what you've seen here is the macro, actually the cell array that we were discussing. It can be a bit more complex, but basically the important part that you see are the cell array here. These are the access control when accessing the array. And this is actually what enforces the lockable region. So you actually send a request, hey, I want to write here, or I want to read this region. This is the block that would probably drop. This is an open source implementation. It's just a reference. So it's just to let you, just to share how this works. The other important part is bus, because in general, this data needs to go up, because it's for the external communication. I mean, because this data needs to be effective, because at rest is just information. It becomes a security feature when it starts being acted upon. So, for example, in ESP32, what you're going to see here, this is just a summary of the list. For example, these are configuration. You see that the bit start and bit count is 1. So there is a low count of bits. So basically you can disable the write on block 1, you disable the write on block 2, disable the read on block 1. This is needed for enabling flash encryption. Then this is also needed for enabling secure boot. And this is needed for disabling JTAG. So this gives you, they are all in block 0. But there is another thing, which are the bulk keys are in an entirely different block. So even just looking at this, we know that probably the logic behind in the OTP controller, the wiring, or even in the memory cell array, is actually very likely different, because you need to minimize, let's say, the die utilization, of course. And these are the read-write protection we were talking about. So this is really pretty straightforward. It should match what we were saying. So the OTP data transfer that we are talking about, they are needed in order to act upon this bit. But reading from OTP every time that you need a bit can be quite slow. So that's why the data is usually transferred to other register, which they are usually referred to as shadow register. Now, this shadow register can be in hardware logic, so that you configure that, or they can be used for faster access from software. So keep in mind that, for example, if you need to know if the secure boot is enabled, and that bit is in OTP, if you every time you need to read that, or a very slow bus, or through a serializer, a sequencer, all these things, it can be very complicated and slow. So basically what you do is that at boot, you transfer this data into register. This is usually called buffered data. There is, of course, unbuffered data, but let's focus on the buffered one, which is always transferred. Some of the shadow registers may be actually memory mapped, because they need to be consumed by software. In general, for example, the ROM code needs to know if secure boot is enabled, and instead of asking OTP, it just reads the dedicated shadow register at the specific address. So every time in your ROM code you see, hey, let me see what is at this address, it's actually usually a read-only shadow register which has been updated by the logic from OTP data. So that is just a mirror of what is in OTP. There are other registers which may be only accessible by hardware logic. For example, the keys that we were discussing here before, the unique keys that go into the hardware, that are device keys, which are not readable by software, they actually stay usually in some of these registers, which are transferred from the OTP to the actual IP. For example, crypto engines will see during boot the population of these registers from the OTP side. So basically, when you start initializing the system on chip, you will see that there is OTP array, the data is always there in OTP bank, and as the chip starts coming alive, the OTP controller starts making its own operation, and it starts sequencing the data according to the logic through common response with the actual OTP array. I mean, this may vary, of course, but this gives you an idea. The OTP data is then transferred to the OTP controller. This is the buffered data we were talking about. And then transferred through the, for example, hardware crypto engine, through the root key register, which now contains the root key of the device. That register is not memory mapped and cannot be read by software. Okay? So this is how you use a key without actually sharing a key in hardware. Of course, there is other information which may go to memory mapped register. There are several, and this will be populated as well. And this is where the software will actually start acting upon. So you see that this data is transferred in terms of information. So the information is transferred several times to the array, to the controller, to memory mapped register, to the CPU when it needs. For example, another glitch that could be possible is basically when the CPU checks if the secure boot is enabled. So you're glitching the software, not the hardware, that says, hey, is this bit 1 or 0? And the software actually sampled that as a 0. But in the register, there is still a 1. What we are talking here is a bit different, because we are interested in focusing on these buses, because all this transfer will happen over buses. So in general, there are opportunities of fault injection that targets hardware only and not software, because at this moment, there is no software being run at this moment. Because the OTP transfer the OTP data is transferred multiple times and across multiple buses with different speed. So basically, a successful glitch of the data of any of those buses may modify the transferred value, while leaving the OTP copies unaffected. So what we are talking about is a one boot only attack, not a permanent, but still possible without doing any software evaluation or targeting any line of software. But if this works, actually that 1 in the OTP becomes a 0 in the shadow register. And so, for example, the software, say, may draw incorrect conclusion. Hey, the secure boot is not enabled. Because the CPU actually reads incorrect value. And not because the read is being glitched, but because the transfer is being glitched before. The same goes for the hardware-based security features, because the hardware logic may be correctly configured. When you disable a JTAG, you are basically transferring a value to a logic gate, to a register, which will set the logic in order to completely cut off the signal of this JTAG. If that register is not populated, there is no JTAG logic disabled. Well, this is all theory. Does it really work? Well, we usually start with doing fault injection characterization. So we actually start to see how a chip behaves according to our needs in general. So in our target, we focused on this module that we discussed, and this is the actual system on chip which is inside, is the SP32, is the first series. No, we have not tested the newer one. Although we think that the concept here, as we have said, may apply to a wide variety of chip and not only to a family of ESP32. So this is a more general talk, which is demonstrated only on ESP32. Our setup overview, basically what we have is, this is our target and this is our probe. Then we have an XYZ stage which moves the probe around. In order to do this, then we have let's say, the brain of our coordination, which actually move the XYZ stage and also communicates to the SP32. So the logic for glitching actually here is an FPGA spider, which basically, according to the configuration, sets and release timers and so on. If you want to see this live, is actually rescued equipment. We use that because we are pretty, let's say, I would say we could call ourselves power user of this equipment. We know that pretty well. So basically, this is the spider. This is XYZ stage that moves our probe around. This is the spider, the logic here. And this is our target. And this is the brain we were talking about. So if you actually map these to the previous picture, it should be easy to see what is doing. And in order to see the connection that we have, this is from the spider. We do have basically two things: the trigger and the reset. So we control the reset, so we can count how long it takes from the reset. So basically, the idea is that every time we reboot the chip, basically we start glitching and see what happens. That's the basic idea. But more specifically, the experiment setup. We enable secure boot by setting this fuse. We set the secure boot key and we also enable read protection. So basically we are not able to read that key anymore. And secure boot is actually really enabled. We program a valid bootloader. The valid bootloader is actually only printing fuses. Nothing more. So it's just dumping the output of the fuses. And that's what we get as an output from our experiment. We just need two other things. While this is running at every boot, we actually scan with our probe the entire chip surface. And we glitch at boot time. We don't know where at this moment, but for sure we want to glitch before the CPU is starting. So we glitch before the first ROM printout. There are, let's say, screenshot the technical details, but this is the generic idea. If you have an oscilloscope, it should be very easy to figure this out, also because there is already material published on this. The goal is for us is to find the vulnerable location. What is a vulnerable location? A location where the dump of the fuses returned any changed bit in the configuration. Any. We don't care. So because we know that in that location, we can do something. So we try to optimize out the space parameters because it's really huge. It's X, Y, Z. So the first thing that we try to optimize out to take this away of the equation is the location. So what you see here is that how we control in the spider in the entire system. Basically, we use still 5Pi from Rescue here, but this is actually a Python script that we create. And what is important is that we classify the experiment based on the data, and that's the important part. For example, in here we say that the results should be colored as green if basically there is a proper reset challenge, and there is and this is actually the response we should have. So if block 0 is in response, so if we have this, and block 2 is in response, so it's 0, then, and you also get the proper boot sequence, then it's green. So it means that we are not being able to be successful. So we do classification of that. The important part for us, so meaning that we bypass the security feature, is that when we have something which is not exactly block 0, but has been different, so we have a regular expression, and also the block 2, maybe we do see something different, and then we see red. So red is good for us, and green is actually we did nothing. Then there are another classification which allows us to map things. So let's see how this looks like. The important part is this classification is not done afterwards, it's done during the experiment. So while the experiment is running, we can build something like this. And basically, what you see are the green and yellow overlapping, meaning that in that location, we both have nothing, or we are able to just reset the chip, and nothing interesting comes. You cannot see that visibly due to the color of the screen, but there are a few red here and a few red here. So, I mean, when you take the slides, you will probably see them a bit better. But we see that when we plot these in terms of how much power we use and where we can actually see the reds, then this is the time that we have. So this means that around this time, we do have successful glitches, basically. And the power of our probe goes from 50 to almost 95. So this means that we also have other parameters, which are the power of the probe that we are using, but also when we glitch. And for us, it's important to confine the search space in general. So this is actually, we start having a look at where are the relevant portion of. If you start zooming on this part, you see there is some aggregation of results. This is really interesting. And you see that from this time to this time is actually between 535 microseconds and 560. So this means that next time that we do the same operation, we can just investigate that area and we don't need to investigate the entire search space. So this means we are much faster, we are much more effective, and we know more. Analysis of the results. What is the data? Because apart from location and red and colors, we also need data. So this is a good block. This is a block where we change 1 bit from C to 8. That's a very good one. Another block where we change 1 bit. One block where we change 1 bit. Block, 1 bit. Block, 1 bit. So this is extremely interesting. So this means that there are locations where we are able to affect exactly 1 single bit in the block 0. So we know that somewhere in the chip, there is a place where this is happening. Oh, this is great. Not only, we also see that basically the timing between, so this is the good one. Have a look at this. This bit here is changed around here. This bit here is changed around here. So there is a very nice timing relationship between which bit you're affecting. Oh, that's quite great, I would say, for fault injection, right? Because it tells a lot when to shoot for hitting what. So basically, we have a successful glitches in a narrow time region. They actually group a specific timing. We have a single bit glitches, and that's beautiful in terms of block 0. So mostly we have 1, which means features enabled, turn to 0. And also we have a strong timing dependency of the affected bits. So basically this means that we can disable security feature, because from 1 we go to 0, but also we can select which one. Oh, that's a bit more interesting than just I glitched this, I think. There is more a pattern here, which is more interesting. So basically we can actually shoot OTP bits while they are being transferred. Well, we first need to reduce the parameter space. So this means that we select the location that we actually see this effect, and we actually move the probe there. We don't move that anymore. So this means that the selection criteria was the number of successful glitches in the kind that we have seen before, so single bit. And also from the next experiment on, we just stay there. We don't move it anymore. So this means that the entire space parameter is gone. 3 dimension. We just look now for power and timing. So let's start by passing security features here. We are reading secure boot key, basically. Let's try to do that. The setup, same as before, nothing has changed, but now we want to glitch the exact bit that enables read protection. So we want to shoot exactly that one. So we program a valid bootloader that prints the fuses. The secure boot key is unreadable, of course, because it's protected. And now we want to read it out. So we need to change this bit exactly during the transfer. And basically we have successful glitches exactly at this time. So basically you're going to see that if you actually shoot around the time with this large variety of power, then you have quite some success, and then you get the entire OTP key out. What you see here is also something interesting, which is also new, for the research until now. So we have block 0, block 1, and block 2. This is the good one I expected. The glitched one, we see block 0 is changed. What is changed is actually this bit, which is exactly the bits that we wanted to change. By shooting at a time, we were able to change that. And that's why we get the key out. What is important is that the success rate. So basically, once we get the parameters around the time, around the power, we just select one and we just measure how effective we are. So the success rate is after fixing this timing and power. Now all parameters are fixed. We don't have anything. We just measure how good we are. And we get a success rate of 1%, where full secure boot key is obtained. And that's an important one. We don't need any brute force. So far the research published until now needed brute force. And I think, that's my personal interpretation, is that the glitching at the voltage was affecting also some bit of the key and not only the configuration. With EMFI, you can be a bit more precise in location. And so we were able to select a location that only affected the configuration and not the rest. So this means that we did not need any brute force. So basically, this means at the speed that we go, we read the SB key within minutes. That's basically the first result we achieved. We want to improve, because, we are not satisfied with this. We want to do this, read the keys, but also do the secure boot bypass. Let's do something better. I'm sorry, this already gave away. It's okay. So basically, we can glitch specific block 0 bits by timing, basically. What is important is that, basically, the read disable bit block 2 here is a bit start 17. So it's quite far, basically. And on the left. And the encrypted secure boot is quite far on the right. So this means that there is time for our logic to shoot, recharge, and reshoot. So this means that maybe we can glitch both. So if they are too close, we don't have time to do double glitch. Actually, we would need 2 probes. That can also be done, but that's for another time. For now, we just do shoot twice with the same probe. Double glitch, the setup, just the same as before. We don't do anything different, but this time we program an invalid bootloader. We program an invalid bootloader that prints the fuses. So this means that the bootloader will not boot. So this means that normally we get nothing out. So we want to bypass the secure boot and print the key. And this will happen only when we bypass the key, as we did before, and then we also bypass the secure boot and we see the output. That's the only situation where we can actually see both, basically. So we need now to change 2 fuse bits during transfer. So we first glitch the read protection. We now know where it is. So we know exactly where to shoot because it's the previous experiment, right? So basically we can actually shoot there. And then the second glitch is timed from this one. So basically glitch more or less in the area that we want to glitch, and from that point on we just count. We know how long because we know where block 0 actually is finished being transferred from previous experiment. So what you see here is pretty interesting in my opinion. This actually looks like the previous experiment. So this is the first glitch that we actually, so the value of glitch delay in a successful glitch. So the value that we use for the first one. Successful glitch also value is this to be glitching both 1 and 2. The second delay, you see, that is constant. So by timing this over the previous one, we just remove away all the jitter. So this means that once we are able to do the first one, we are also very likely to be able now to do the second one, because we now know, after this experiment, where it is. So this is becoming pretty precise in general. And so this allows also, there's something interesting here which we didn't anticipate. Basically, it seems that our successful glitches, double glitches, occur in group. So this means this is an ID. Maybe between 100 and 200, we get a batch of successful. Then after 50,000 attempts, we get another batch. Then after another 50,000, we don't know this. Why? There are guesses, maybe the room temperature of the day, that we actually see that happening, or a SoC status. We don't know exactly, but we see this interesting pattern. In this case, we are still successful. The success rate dropped to 0.5%. We are still fine with that. We don't care, because we can still bypass that within an hour, which is still perfectly doable. So that's why we think the success rate for comparing fault injection experiment, let me say that openly, sucks. Because it is not related to how fast you go. I mean, if you have 1% and you do 10 experiments per year, it takes a long time. But if you do 1 million experiments per second, 1% is nothing. So that percentage of success rate is useless. Unfortunately, it's the only metric which is used in academia. Well, there are considerations over there. Now, can we bypass secure boot and flash encryption together? Well, we did try it a lot. Unfortunately not. We were not able to do that. But we got an idea, basically. And what if we actually glitch the JTAG? I mean, if we are able to glitch the JTAG, which is usually closed when you have secure boot and flash encryption. So in practice, secure boot and flash encryption also enable close the JTAG. But if you open the JTAG, you're also able to run code. So secure boot is automatically bypassed. The only question which is left is if you could bypass also flash encryption. Let's see. So basically, I'm sorry, it's my fault maybe. Let's try to continue for a moment. Okay, so basically we do set secure boot as before. We do enable flash encryption, and we also make sure that JTAG is disabled. We program a valid bootloader and print eFuses this time, okay? And the idea is basically we want to see when the JTAG interface is open, because the only thing which is left for us are two things. One, if we are able to open JTAG, and second, when the JTAG is open, are we able to read plain text firmware from the flash encrypted? Well, because actually once you open it, you actually bypass secure boot. This is our classification. Our classification goes set this 54 to 115. Thank you. And basically, this is where we are. We know that we have disabled the JTAG at this point. We just check if JTAG disable is unset, and actually we do have successful glitches again. So, and they are all scattered to a nice and precise line, and the success rate that we are discussing here is still within a few minutes. So this means that with one single glitch, we are able to bypass secure boot and flash encryption by glitching something else that allows us to bypass the secure boot and to read the plain text firmware. So maybe when you want to bypass a security feature, you don't need to target a security feature. So this is something that actually invites people to think along the attack and the design. I would like to show you, because I know that I'm pretty running out of time, but I promise that it will be quick. And let's do that. So Nick is actually doing this. Well, actually say hi to you, everybody. And basically, we are going to show the demo right now. First, we need to check if JTAG is actually really closed. And the first, what do we do? We actually connect OpenOCD and see if we have any response from the top, which we don't have. So this means that it actually is closed, because this chip has been programmed with JTAG disabled fuse. So it's closed, so we start glitching. I will start to show you a few things. So this is the output that we get. As soon as we get a successful glitch, we stop. As soon as we stop, we just check and connect with the JTAG interface and see if you can read plain text firmware. Now, to make this a bit faster, let me go back because I know where it is. So, and there you go. There is one glitch which is red. The experiment stopped. Basically, that's what we're implementing in the logic. And let's see and verify. You need to know first if it's really open. So the tab should connect now, which actually it does. And the second part is that we need to read flash. The flash is now memory mapped at a specific address, basically, which is 3F400000. Now we connect to OpenOCD, so this is, usual stuff. Then we stop the chip, and we try to read the memory from their address. We actually read a bit after, because first there is header and so on. This is where the app is, and you see that this is fully in plain text while the flash encryption is enabled. So basically, let me stop this and going back to the presentation, because I would like to continue. So what we did here is that this actually was in plain text while it should have been encrypted. And what can we do in order to fix this? Well, we use firm for describing the attack. We use the equipment, EMFI, we flip data bit, and we target OTP by timing. And we use this framework for describing an FI attack. There are more on our website. But we also use this for a countermeasure, because depending where you apply the countermeasure, you can prevent, we inject, you can detect your glitch, you can detect your fault, you can prevent your exploit, you can kill your goal. So there are many things which can actually apply at different point in time. For example, if you want to prevent the injection, you use EM shield or clock glitching. You need internal clocks. The package allowed to pop and pop, so package on package may help you against the EMFI. And there are things. The interesting part is that maybe we need bus error level detection, bus level error detection, checksum, doing multiple transfers. So there are a few countermeasures which can happen. So in a nutshell, we have seen how the OTP data transfer can actually completely compromise SoC security. The fault injection attack here is against a pure hardware implementation. There is no software involved here. And we actually bypass SoC security feature before any software is executed and before actually any CPU is released from reset. We also found out there is strong timing correlation between OTP data and which allows for powerful attacks. We broke the read protection, basically. We do a debug glitch for breaking the secure boots in addition. And we actually bypassed flash encryption secure boots by targeting something completely different, which is the JTAG. So, in a nutshell, basically we think that these kind of attacks are often overlooked. Fault injection are usually applied in the software, execution of software. The point is that mutability at rest does not imply integrity in transfer. These are completely different things. The design may not include hardware protection nowadays, because FI is almost always used for targeting software, but we think that design level mitigation are possible. I'm sorry if it took a few minutes more, but I hope it was interesting, and I'm available for questions.
Okay, we need to be a bit quick. So,
Okay, thank you very much for your presentation. It's very interesting. I think in 2020, Espressif announced the ESP32v3, the Eco version. I don't know if you tried to.
Not yet.
Not yet. Okay. Okay. Thank you.
You're welcome.
Since this OTP data is being transferred over the bus, how hard will it be for somebody to read the keys by probing just the buses?
I think that it can be done. We expect that some buses, especially the niche one, are not really that fast. But I think that probably Olivier is the right person to better answer this question. But I think it could be done in practice, depending on, let's say, chip layout and all the different things that allow you to do micro-probing. So if you can do micro-probing, then for sure you can extract the key. That's more or less the answer. Thank you.
One more quick question.
I'm available for further question anytime. Yeah, I will take the question now. Yeah, thank you.
Thank you once again.